quite as far as I wanted to yesterday, so I just want to pick up a couple of things that I didn't finish talking about churn insulators. Okay, so yesterday we talked about the quantized Hall effect with Landau levels, and realized that if you could get a churn number, then you get the same kind of effect. And so the question is, how can you make it happen? And this goes back to an old idea by Duncan Haldane, who wrote down a very simple model on a honeycomb lattice, okay, where he realized that he could get a non-zero churn number. And so this is a very nice model, but there's another way to get at it, which is very physical and very nice, which is the idea of inverting a band. And so this is what I want to focus on. So if you have a trivial insulator, which is what you usually have, then one route to a topological insulator is to go through a band inversion transition where the conduction band and the valence band sort of cross each other. And provided you do it correctly, then you can go through a quantum phase transition into a inverted topological insulator. So I just want to show you a simple model where this happens. And this model it has the same sort of structure as the Su-Schrieffer-Heeger model that I told you last time, where you can think of it as just a 2x2 matrix block Hamiltonian. And so what you want is you want to have a so it's a two-band model, so it's a 2x2 matrix, and so I have one band which is the conduction band, another band which is the valence band, and so I want them to have symmetries where one of them is like an S state and the other one is like a px plus ipy state, and then the kinds of of course there's a simple tight binding band for each one, which is the tau z part, the diagonal part, and then they're coupled together using both tau x and tau y. That's what the p plus ip symmetry allows for you. And so if you do that, then when this delta E is very large, then it's uninverted, and it's just a trivial insulator. But then as you let delta E get smaller, these bands cross each other. And what you can see is that if you think of this Hamiltonian as describing a vector D dotted into the Pauli matrices, then in the uninverted case, then D is sort of always basically in the z direction, so it doesn't sweep out any solid angle as a function of of K in the two-dimensional Brodmann zone. But in the inverted case, then what happens is the D vector as a function of K in the two-dimensional Brodmann zone sweeps out the entire sphere. Okay, and so I told you that the Berry phase is the solid angle on the sphere. So the Berry phase per unit area in the Brodmann zone is just the solid angle by the little area element. And so if you add all that up, then the churn number is just the number of times that the D vector wraps around the sphere. Okay, so it's sort of a winding number for the. So in the two-band model, the churn number is very easy to recognize. It's just a winding number for the mapping from the Brodmann zone to the Bloch sphere. Okay, so this is a very nice model, and this is a paradigm for how you can get to a churn insulator. Is you want to go through a band inversion transition. It's actually very nice to think about the continuum limit for this model. It turns into something even simpler. So if I imagine that the gap is very small, so all the action is around the band crossing point, then you can expand for small k, and then what you get is something that has the form of a Dirac Hamiltonian. Okay. Now, so if you expand only to linear order in k, then you have a kx split ky multiplied by the Pauli matrices, and you have a mass term tau z, which depends on the band inversion. I expanded to order k squared, and it's the reason why it's important to expand to k squared, because if you don't have the k squared term, then the model doesn't know which side is the topological and which side is the non-topological side. Okay, so it's the regularization. So for large k, this model, for large k, the Hamiltonian it goes to just tau z. So it has a well-defined large k limit. So it's regularized. So it's this term that tells you which sign of M is the topological state and which sign of M is the trivial state. Okay, so this is, so this is a very nice, this is sort of the simplest model that you can write down that describes a Chern insulator. Okay, so that's what I wanted to say about that. So then I want to, so what I want to finish up everything I have to say about topology without symmetry. Okay, and so one can generalize this notion of a Chern insulator to higher dimensions. Okay, so for instance, in 4 dimensions, there's a 4-dimensional version of this Chern insulator, 4-dimensional integer quantum Hall effect. And you do the same thing. So you define a connection, but now what you need to do is you need to have multiple bands. So your connection then is going to be a matrix. So it's a non-abelian Berry connection. Okay, which is, which one can define. And if one defines that, then one can define the Berry curvature, and since it's non-abelian, it has these 2 terms. Okay, so in 4 dimensions, one can define the second Chern number, which is sort of the integral of f wedge f. So f wedge f is a 4 form that you can integrate over a 4-dimensional Brillouin zone. Okay, and so it's the same sort of deal, and so this integer is also this second Chern number is going to be an integer, and that defines a kind of 4-dimensional Chern insulator. And the thing, so in 4 dimensions, of course, there's a 3-dimensional boundary, and so the boundary of the 4-dimensional Chern insulator is a 3-dimensional chiral fermion. Okay, so it's like a Weil semi-metal, but it only has 1 Weil point. Okay, and that, of course, that's impossible. There's a doubling theorem that says in 3 dimensions, well, the Weil points have to come in pairs, but you can violate that by having the boundary of some 4-dimensional Chern insulator. Okay, and so let me just say, so this extends to even more dimensions. So and there's a very nice pattern. So in even dimensions, you can always define a Chern number by just doing f wedge f wedge f wedge f, as many times as you need, and that defines a Chern number in all even dimensions. And then in odd dimensions, I did 1 dimension last time with the Sushri-Verheugen model, where of course I had to have symmetry, but if I have the chiral symmetry, then I could define a kind of winding number, is the winding number of this D vector around the circle. And that generalizes in any odd dimension. One can define a kind of winding number when you have chiral symmetry. Okay, and so there's this pattern that you have, and this periodicity, it sort of looks the same if you add 2 to the dimension. And so this is some deep mathematical thing that I only sort of dimly understand, but it's called Bott periodicity. Okay, so and this is going to show up again later in the talk in a slightly more complicated version. Okay, all right. So so this is the story when all you have is topology and you don't have any symmetry. So now I want to talk about symmetries, and in particular, I want to talk about 2 kinds of symmetries that are important to think about, which are time reversal symmetry, and then the particle hole symmetry that a superconductor, the BCS model of a superconductor has. Okay, and these 2 kinds of symmetries sort of go together, so when you have this symmetry, so for instance time reversal symmetry, then of course you lose things. Okay, you can't have a Chern insulator with time reversal symmetry because if you reverse time, then the edge states don't know which way to go. Okay, so a Chern insulator cannot respect time reversal symmetry, but you get something new. Okay, which is you get that it's possible to have a Z2 topological insulator. Okay, and so I'll tell you about this, and then in a superconductor. If you describe it in mean field theory, it's a free fermion problem, but it's a free fermion problem with a special kind of symmetry. Okay, and this is a symmetry. It's sort of like the chiral symmetry that I told you about. It anti-commutes with the Hamiltonian, But in this case, it's going to be anti-unitary. I'll tell you what that means. And so this is then going to lead us to topological superconductivity, and then I'm going to put this together into a sort of mathematical package that is sort of like the Bott periodicity picture that I showed you before, where these sort of unifies these kinds of things and gives you all the possibilities. Okay, and so then, assuming there's time, I'm probably going to run out of time, but I'm going to say some words about topological superconductivity. If I run out of time with this, then I think other speakers are probably going to cover some of this material as well. So we'll see how far we get. I think I'm going to opt for going slow so that everybody gets something rather than trying to say too much and then get nothing across. So that's going to be the plan. Okay, so let's talk about time reversal symmetry. So of course, time reversal symmetry is what happens, if you want to describe what happens if you run a motion picture backwards, right? So you're reversing time. But in quantum mechanics, time reversal symmetry is it's a symmetry, but it's not like ordinary, because the time-dependent Schrodinger equation has an I in the time derivative term, and so time reversal symmetry is a symmetry that involves complex conjugation. Okay, and so an operator that involves complex conjugation is a unitary operator with a complex conjugation is called anti-unitary. Okay, so the time reversal operator does two things. It takes the complex conjugate and it also flips the spin. Okay, or it does a 2 pi rotation of the a pi rotation of the spin, so this is what time reversal does, and it has a very special property, which is if you do time reversal twice, okay, then it squares to -1. And so you can see this, if you do this twice, then the square of the time reversal operator is rotating the spin by pi and then pi again. So it's like a 2 pi rotation of the spin. That's what the square of the time reversal operator is. And for half integer spins, a 2 pi rotation gives you a minus sign. So that famous minus sign is the minus sign here. Okay, so and this minus sign has it seems like it's a pretty simple thing, but it has a very deep consequence, which is called Cramer's theorem. Okay, and so what Cramer's theorem says is that if you have time reversal symmetry and you have a half integer spin, then every state has to be at least twofold degenerate. Okay, so every state has a partner at exactly the same energy. Okay, and so let me, the proof of this is very simple. So let's assume that we had a state that wasn't degenerate. Okay, so it's the only state at that energy. Now, since the time reversal operator commutes with the Hamiltonian, if I act the time reversal operator on that state, then that has to also be an eigenstate. And since it's not degenerate, then it would have to be the same state, up to some constant. Okay, so that's true. So then we can do it again. I apply time reversal again, and again I'm going to get the same state, but since it's anti-unitary, instead of multiplying, when I do that, I'm going to multiply by c, but then I also take the complex conjugate, which is c star, and so I get the magnitude squared of c. Okay, and the contradiction, therefore, is that the magnitude squared of c cannot be equal to -1. Okay, so that means that the assumption that it was non-degenerate had to be wrong, and so every state has a Cramer's partner. Okay, and so this fact is what is at the root of the fact that topological insulators can occur. Okay, and so the way I want to motivate topological insulator, I want to do the same. I had this thing that I said yesterday that all the topological band theory, band structures that you can have, they're all different versions of splitting the indivisible. Okay, and so I showed you that a Chern insulator you can think of as you have a one-dimensional, just a one-dimensional wire which has right movers and left movers, which have to be on top of each other. But a Chern insulator is a way of separating the right movers and left movers and split them apart. Okay, and so I want to do the same thing. Now, of course, you can't split the right movers and left movers apart in a time reversal invariant way, right? Because the right mover by itself, goes to a left mover under time reversal. Okay, but if you have spin, then you have upspin and downspin electrons. Okay, and so the one-dimensional wire is going to have upspin and downspin right movers and left movers. Okay, and so that offers us the opportunity to split those in a way that respects time reversal symmetry. Okay, and so that's what a Z2 topological insulator is. Okay, so on the top edge it has the upspins going in one direction and the downspins going in the other direction. So if I do time reversal, then the upspin turns into a downspin, but the right mover turns into the left mover. So these edge states are time reversal invariant. Okay, so time reversal allows it. Time reversal also protects it. You see, the thing is that on this edge you have both a right moving and a left moving branch, and they cross each other. Okay, and the first thing you learn when you learn quantum mechanics is that degeneracies never happen by accident. Okay, and so any small perturbation will lift the degeneracy, and a crossing will turn into an anti-crossing. Okay, unless there's a symmetry, and so this is what time reversal symmetry does: is it protects that crossing, because the point where these two bands cross each other is at k equals 0, and so these two states are a Kramer's pair. Okay, and so time reversal protects it. And the simplest way of thinking about this two-dimensional topological insulator, or also called a quantum spin Hall insulator, is to think it's just two copies of a Chern insulator, one for the upspins and one for the downspins. They have opposite Chern number. Okay, so that respects time reversal. Okay, so that's the simplest thing that one can do. Okay, and so so then there's a question you can ask, which is what are the topological classes? So for a Chern number, you can have any integer. You can have any integer number of these. Any integer number of chiral edge states. Okay, so you can have any integer Chern number. So what's the topological? What are the topological classes for the Z2 topological insulator? And obviously it's Z2. So what I want to explain to you is why there are two and only two topological classes. And again, I'm not going to get into the bulk formulation of the Z2 topological invariant, but what I'm going to do is I'm going to draw a picture for you that should convince you that there are two and only two possibilities. Okay, and so I'm going to do that by thinking about the edge state. And so on the edge of a two-dimensional insulator, it's always possible that you have there's going to be a valence band and a conduction band that are separated by a gap. It's always possible that you could have bound states that are bound to the surface that are inside the gap. Okay, but the thing that is that if they're time reversal invariant, then at k equals 0, they have to be Kramer's degenerate. There have to be a pair of states. Okay, and if you look at the boundary of the Brillouin zone at k equals pi, then so of course pi and minus pi are the same point, because the Brillouin zone is a circle, and so at pi the states also have to be Kramer's degenerate. Okay, if you're in between, then they don't have to be degenerate, because k and minus k are different points. Okay, so the Kramer's partners are at k and minus k. Okay, I only drew half the Brillouin zone here because it's a mirror image on the other side. So now you can understand why there are two and only two ways you can do it, because there are two and only two ways that the Kramer's pairs at k equals 0 and k equals pi can connect up with each other. Okay, either they connect up pairwise, okay, in which case you don't have to have them. You could just push these states down into the valence band and these up into the conduction band, and so the edge states are not necessary. You could have them, but you don't have to. But if you do have them, then there's going to be an even number of them. Okay. Whereas the other possibility is that the Kramer's pairs sort of switch partners when you go across. Okay, and in that case, you sort of see this pattern where it goes zigzag up, and there's no way you can get rid of this. Okay, provided you keep the Kramer's partners at the boundaries. Okay, and so in this case, you're guaranteed to have an odd number. Of course, it doesn't have to be 1; it could be 3. But so this sort of explains how you know that there are 2 topological classes of 2-dimensional time reversal invariant insulators. Okay. So so it's nice to write down. Okay. So I said I wasn't going to say anything about the bulk formulation, but I am. So so how do you know, given a band structure, which one it is? Okay. And so this is a math problem that I thought about a while ago, and it was a hard math problem. I solved it, but I'm not going to tell you the general solution. I'm going to tell you a couple of simple things that you can know. So the simplest thing is that if you just have 2 copies of a Chern insulator, then each Chern insulator has a Chern number. Okay. Now they have to be the same. The Chern numbers of the upspins and downspins have to be equal and opposite. So in that case, the Z2 invariant is just whether that Chern number is even or odd. Okay, so if you have an odd Chern number, then it'll be, for instance, if it's 1, then that gives you this. And in this sort of independent up and down spins, this is the reason we called it a quantum spin Hall effect, because if you apply an electric field, then the upspins sort of go this way and the downspins go the other way. Okay, so there's no charge Hall effect because they cancel each other, but there is a flow of spin. Okay, so but this is kind of a contrived model. There's no physical principle to tell you that SZ should be conserved unless you have an absence of spin orbit, but you need spin orbit in order to do this. Okay, so this is sort of a model thing. Now there could be crystalline symmetries which are sort of like SZ conservation. So for instance, if you have a reflection symmetry, reflection symmetry can do something like this. Okay, but in general, you don't have this, and so you can ask, well, are there other ways that you can know what the invariant is? And so there's another very simple method for recognizing the Z2 invariant if you have a crystal that has inversion symmetry. Okay, because if you have inversion symmetry, then in the 2-dimensional Brillouin zone, there are 4 points where k and minus k are the same point. 0 is the same point, but pi 0 and pi and 0 pi, they're all invariant under inversion. And so the eigenstates at those points are either going to be even or odd under inversion. Okay, so there's these parity eigenvalues. And basically, the Z2 topological invariant is just the product of all of those parity eigenvalues for the occupied states. Okay, and so this allows a method for sort of reading off what the Z2 invariant is, provided you have the symmetry data of the band structure. Okay, and actually for the 3-dimensional topological insulator, this is the way that I was able to identify the first topological insulator that was identified, which is an alloy of bismuth and antimony. So that was the trick that we used to do that. Okay, so now in general, though, maybe you don't have symmetries, and there's a pretty highly developed technology now for determining the Z2 topological invariance for a general band structure. Okay, so this is something people know how to do. I'm not going to go into the details of these things right now, though. Okay, so a simple model for describing a two-dimensional topological insulator is this same kind of band inversion paradigm. Okay, but now we're going to have a band inversion of it's sort of doubled because we have both up and down spins. Okay, and so this is a model that was written down by Andre Bernavig, Hughes, and Zhang, and it has exactly the same structure as this continuum model for the Chern insulator that I showed you before. Okay, and it describes a inversion between a sort of S-like state and a P-like state, and of course this is what happened in these mercury telluride quantum wells that Lawrence Molenkamp studied, and so this was sort of the beginning of the topological insulator field with these experiments on these systems. Okay, so I think that's all I want to say. Yeah, I do want to say one more thing about topological insulator, the three-dimensional version. Okay, and all I want to say about this is that again, it's a version of splitting the indivisible. Okay, and here the impossible thing that's at the surface is having a two-dimensional massless Dirac cone with just a single Dirac cone. Okay, and that's something it's sort of half the degrees of freedom of an ordinary electron gas that has up and down spins. Okay, and this is something that is impossible for a purely two-dimensional time reversal invariant system. Okay, and there are a couple of things that are special about it. So the surface state, in general, if the Fermi energy is away from the Dirac point, the surface state is the Fermi surface is going to be a circle. Okay, but the spin is sort of correlated with what direction you go. So it's non-degenerate. There's just a single state on the Fermi surface, whereas usually you have both up and down spins. Okay, so it sort of has half the degrees of freedom of ordinary two-dimensional electron gas. And if you go around the Fermi surface, notice that the spin rotates by 2 pi. So that means the wave function picks up a minus sign, a minus 1, or a pi Berry phase. Okay, so that pi Berry phase, is allowed, because pi and minus pi are the same, so it respects time reversal. Okay, but it's distinct from a Berry phase of 0. Okay, and this pi sort of leads to some interesting features of this. So one way of describing it is a quantized magnetoelectric effect. So there's something called a theta. There's a number called theta, which is equal to pi here. Okay, and what that's related to is it's related to the fact that if you were to break time reversal symmetry on this surface, then you could open up a gap in the surface state, and then that would have a half quantized integer quantum Hall effect. Okay, and that's what this theta equals pi is telling you. And again, this half integer quantized, it's impossible to have a fractional integer quantum Hall effect. Okay, so this 1/2 is impossible, but it is possible on the surface of a topological insulator. Of course, you can't have the top surface without also having the bottom surface. Okay, and so that's the way you get around the impossibility of having. You always have 1/2 plus 1/2. Okay, so and the magic of this is that these surface states are impossible to get rid of unless you break time reversal symmetry. Okay, so they're impossible to localize, and what they are like is of course in the quantum Hall effect you have an energy gap, Landau level energy gap, but when you go from one plateau to the next, you go through a quantum phase transition, and at that transition, then the states are extended. Okay, and so what this surface of a topological insulator is it's like the plateau transition between two quantum Hall states. The thing that's special about this is that time reversal symmetry tunes you to be precisely at that transition. Okay, so the two quantum Hall states on either side are related by time reversal symmetry. Okay, and so time reversal symmetry sort of tunes you to be exactly at the transition. So that's the thing that's special about the surface of the three-dimensional topological insulator. Okay, so now I think this is all I was going to say about time reversal invariant topological insulators. And so now what I want to do is I want to sort of using the same kind of language and the same methods, I want to describe topological superconductivity. Okay, and so the now of course we heard about superconductivity a little bit yesterday, and it's an intrinsically interacting problem. Okay, you have to have an interaction in order to get a superconductor, but the BCS model is remarkable because it allows you to understand almost everything about a superconductor using mean field theory, which turns the interacting problem back into a single particle problem. Okay? But it's a single particle problem where you have to pay a little bit of a price because you have to allow yourself to have the anomalous terms where you have two electron annihilation operators. Okay, and that's allowed because you have a condensation of Cooper pairs. Okay, and so in order to describe the sort of single particle quantum mechanics problem that the BCS mean field theory describes, you have to allow yourself to have these psi dagger terms in the Hamiltonian. And so the way to do that, you can write the Hamiltonian as a matrix as a 2x2 matrix that involves psi dagger psi and also psi dagger. Okay. And so it's these off-diagonal terms that give you the superconductivity. Okay, yeah?
When you say that interactions are necessary in the real problem,
yes.
Is it interactions of electrons with other electrons, or is it interaction of electrons only with phonons? Do they need to
yes.
interact with each other?
Yes. I mean, look, if you have interaction of electrons with phonons, then that mediates an interaction between electrons and electrons. So the thing you need is you need to have an interaction between electrons and electrons that's attractive. Usually you have repulsive interactions, and repulsive interactions don't take you towards superconductivity. But if you have an attractive interaction, then the instability is towards the superconducting ground state. Yeah, so it's the attractive interaction that wants to bind the Cooper pairs, basically. But that physics is swept under the rug in the mean field theory. Okay, and so we're going to just posit that in mean field theory we have this anomalous term with that basically turns a pair of electrons into a Cooper pair, which is condensed. Okay, so we're writing this Hamiltonian now as a 2x2 matrix, and we've done something very special here because notice, if I turn off the superconductivity, if I turn off the delta, then I have two copies of the original problem. Okay, one with H and one with minus H. Okay, so I've taken my original band structure and I've made another copy of it where I've turned it upside down in energy. And so the model I'm considering is the combination of those two. Okay? So that model has, just by construction, it has energy goes to minus energy symmetry. Okay? It looks exactly the same if I flip it upside down, right? And so we had to do this in order to be able to put these terms in. Okay? We had to double the Hilbert space basically. Okay, and so this Bogolubov-de Gennes Hamiltonian has an intrinsic symmetry, an intrinsic particle-hole symmetry, and in particular, this particle-hole symmetry is a anti-unitary particle-hole symmetry. Okay, so it involves complex conjugation, and so there's so if you look at if the Hamiltonian, which is tau x times complex conjugation, then you can see that this operator anti-commutes with the Hamiltonian. And whenever you have an operator that anti-commutes with the Hamiltonian, you're guaranteed to have a particle-hole symmetric spectrum. Okay? So, it's an anti-unitary operator, involves tau x. So if you do it twice, you should get back to where you started. And if you square this operator, unlike the time reversal operator, it squares to +1. Okay, so that's a feature of this intrinsic particle hole symmetry of a Bogoliubov-de Gennes Hamiltonian. Now, so I made a big deal last time about the fact that there's sort of two levels that you can think about these theories on. You can think about them on the single particle quantum mechanics level. Okay, and on the single particle quantum mechanics level, the problem we have is just like the problem of classifying band structures. Okay, we have a Hamiltonian. Now it's twice as big, but it's still some band structure. It's a block. You can have a block. You have Bloch's theorem. You can talk about the band structure. So it's a block Bogoliubov-de Gennes band structure. But we're going to so the interesting question then is, what are the topological classes that you can have? Okay, and so that's a single particle quantum mechanics problem that we'll solve. Okay, but you see, there's also, so you can describe the single particle eigenstates, but the many body ground state, right, is the state where you fill up the occupied single particle states, and then you have a many body state. And so there's something special here that happens with this particle symmetry. Because notice that when I write it like this, I have both psi and psi dagger on the left and the right. Okay, it's the same operator. So what this means is that I can imagine a state where I start with the ground state and I add a fermion into the positive energy state, into the conduction band. Or I can imagine a state where I remove a fermion from the negative energy state. Okay? Now, in an ordinary band structure, like a semiconductor, those are two different states. I add an electron or I remove an electron. Those are two different states. But in this Bogoliubov-de Gennes theory, they're the same state. Okay, because I doubled it, but the real theory isn't doubled. Okay, and so adding a particle in the conduction band is the same operation as removing a particle from the valence band. Okay, and so this is an important thing that one has to keep in mind when you're doing the BCS mean field theory. Okay. So now, these Bloch Bogoliubov-de Gennes Hamiltonians have this intrinsic symmetry, and so now what we have is we have a topological classification problem, which is sort of the same kind of thing that we had when we had time reversal symmetry. Okay, and so let me sort of give you the simplest thing you can think about, which is in one dimension, and I told you that the way we can sort of figure out what kinds of topological classes you can have is you can think about the boundary. And what kind of impossible things can you have on the boundary? Okay? And so if I think about a one-dimensional superconductor, okay, and imagine there's an energy gap. So there could always be states localized at the end. Okay, there could always be some state that decays exponentially into the bulk that is localized at the end. That's allowed. Okay? But the thing that we know is that due to this intrinsic particle hole symmetry, if I have a state at positive energy, then it has to have a partner at negative energy. Okay, so so these bound states have to come in pairs unless they're at E equals 0. If they're at E equals 0, then this is still particle hole symmetric, but this one state is its own partner. Okay? It's just like what happened in the Schrieffer-Heeger model. Okay? Except now, instead of the particle hole symmetry being a fake symmetry, now it's an intrinsic symmetry. Okay? So, so if you have this zero mode at the end, okay, then you can't get rid of it. Just like in the Schrieffer-Heeger model. You can't get rid of it because if you tried to move it away from 0, then its partner would have to appear out of nowhere. Okay, so the only way you can get rid of it is if you close the bulk gap and go through a quantum phase transition. Okay, so the zero mode is topologically protected. Okay, Okay, so and so now we have this one state, okay, which I can imagine I can either add a fermion or remove a fermion from it, okay. But remember, in the Bogoliubov-de Gennes theory, there is this intrinsic redundancy in that, because remember, adding a particle at E is the same as removing a particle at minus E. Okay? And so for this zero mode, that means that adding and removing a particle into the zero mode is the same thing. Okay? And so this is what a Majorana bound state is. Okay? So the particle and the antiparticle are the same. You know, one way you can think of it is that if you have two of these Majorana bound states, so of course, you know, if you have a one-dimensional superconductor, there's going to be one end, there's also going to be the other end. Okay, it's kind of, you can't have just one end without having another end. Okay, and so these two Majorana fermions, you can combine together. So you can sort of think of a Majorana fermion as being either the real or the imaginary part of a Dirac fermion. So, you know, Dirac fermion, you have psi and psi dagger. Okay, and you can combine them, you know, and take this either the real or the imaginary part, or equivalently, I can write, you know, psi is equal to, you know, gamma 1 plus I gamma 2. Okay, and so what this and this is an ordinary, you know, psi is an ordinary Dirac fermion, and so it defines a Hilbert space with two states. Right, because that Dirac fermion mode can either be occupied by a fermion or not occupied by a fermion, and those are the two states. Okay, and so this pair of Majorana modes defines a single two-level system. Okay, and so that's the you know, that's the beauty of the Majorana. And so again, we can think of this as a version of splitting the indivisible. So ordinarily, if you have a two-level system, you know, a two-level system is, you can't split it in half. How do you split a two-level system in half? Okay, but what the one-dimensional topological superconductor allows you to do is to do that. Okay, and so then the two halves are in, you know, different places, and they're separated by a gapped topological phase. Okay, so right. Okay, so you know, then there's the question: how do you make this happen? And so so one can write down a very simple model for this. And since I showed you the Su-Schrieffer-Heeger model yesterday, I'm going to show you basically the same model again, but now it's going to be called the Kitaev model. So what the Kitaev model is it's just a one-dimensional chain, okay? But I'm going to make it a superconductor. Now, the simplest theory is just one-dimensional spinless fermions. So I have to. So if I want to have some anomalous term, I have to have. It has to be like a p-wave superconductor where I have the term which creates a pair of electrons on neighboring sites, and it has to be p-wave because the electrons are fermions. They anticommute. Okay. So, but if I have this one-dimensional p-wave superconductor, I have a regular hopping term, I have the anomalous term, and I have a chemical potential. So, so then I can write this as just as a 2x2 matrix. Okay, so I just you know, Fourier transform this, and so I can write it again as you know, a 2x2 matrix, which I can think of as a D vector multiplied into the Pauli matrices. Okay, and it has exactly the same kind of structure that the SSH model I had last time, and so in particular, due to the particle hole you know, symmetry. Well, so in this simplest model, it doesn't involve tau y. It only involves you know. So there's basically a winding number that one can define that goes around. Okay, and so there are two phases of this model, and those describe the you know, the trivial insulator. Okay, where you can think of this as you know, sort of very tightly bound Cooper pairs, or you can have a weak pairing phase, which is the topological phase. And so what I want to, again, it's just like the SSH model, except the symmetry is a little bit different. Remember, in the SSH, we could have either the unitary particle hole symmetry, or I could have the reflection symmetry, which relates K and minus K, and that protects the topological states of the Schrieffer-Heeger. So here, what we have is we have the anti-unitary particle hole symmetry, and that also relates K and minus K. It has a little bit different structure than the unitary particle hole symmetry does. Okay, this symmetry also, protects. We know by thinking about the N modes that it has to define a Z2 topological invariant. Okay, so this is the one-dimensional model. Now, one can make an even simpler version of this model. Okay, if we think about each site here has a CNC dagger. It has a Dirac fermion. I can think of each site as being a pair of Majorana fermions. Okay, and so I'm going to write the same model, but I'm going to write it a little bit differently. So inside these green circles, I have two dots which describe the two Majorana operators that make a single electron annihilation operator, and so so then we can write down the Hamiltonian in terms of these Majorana modes, okay? And if we go to a particular point where there are three parameters in the model. There's the chemical potential, the hopping, and the delta. If we go to a particular point in that three parameter space, so it's only as a function of two parameters, then the second neighbor interactions will be equal to 0. And so all we'll have is the first neighbor interactions. And then it looks exactly like this dimerization problem that we had in the SSH model. Okay? Though now, the dimers are not pairs of lattice sites. Okay? The dimers are between, I'm splitting each lattice site into two sites. Okay, and so in the trivial superconductor, what's happening is that the Majorana modes. What's happening is that the Majorana modes are pairing up on a single site. Okay, and that's the trivial superconductor. In the topological superconductor, they're pairing up between the sites. Okay, and if they pair up between the sites, then you know that at the end there's going to be a leftover one that's not paired, and so this is the unpaired, Majorana 0 mode. Okay, and so so this is a nice picture. All you need to do is to look at the picture, and you understand what a topological superconductor is. Okay, so this is a very nice model. Okay, so this is a one-dimensional topological superconductor. So one can ask, are there higher dimensional versions of this? Okay, and so a two-dimensional topological insulator. So if you think about what could happen at the edge, you can imagine you could have a chiral mode that respects the particle hole symmetry. Okay, and so this is what's a chiral Majorana mode. So if you have a one-way edge state where the operators at plus k are related to the operators at minus k in this way, so that would respect the particle hole symmetry. So this, in principle, you can have this, okay, but it's impossible by itself. So it must be what happens at the boundary of a two-dimensional topological superconductor. And so there's a simple model that one can write down. It's just like a Chern insulator. So what it's like is it's like a Chern insulator in the Bogoliubov-Dejean theory. Okay. And so the model, the Reed-Green model so Nick Reed introduced this idea, and it's basically the same band inversion model of a Chern insulator that I showed you before. Okay? But now it's in the context of a Bogoliubov-de Gennes theory, so it has this intrinsic particle-hole symmetry. Okay, and so, but other than that, it's kind of the same model. And again, in order to have the sort of open up the gap everywhere, you have to have a superconductor that has a px plus ipy behavior. Okay, so you have to have a time reversal breaking superconductor. Okay, and so you have a P plus IP. And so you can write down this continuum model. You can also write down a lattice model. And again, this lattice model is the same lattice model. It's just like the BHZ model or the lattice model that I showed you for the Chern insulator. Okay, and it has the, and when I write it like this, I can think of it as a D vector dotted into the Pauli matrix. And again, you can just read off the Chern number by counting how many times does the D vector wrap around the sphere as a function of the two-dimensional Bro-1 zone. Okay, and so in the strong paired phase, it does not wrap around the sphere. In the weak paired phase, it does wrap around the sphere. Okay, so that's a two-dimensional superconductor. Now, another thing about the two-dimensional superconductor, so we have boundary states which are one-dimensional chiral Majorana fermions. Okay, you can also get zero-dimensional Majorana bound states on vortices. And so the simple way to see that is if you have a vortex, you can imagine you can have a vortex if you drill a big hole in the superconductor and put a magnetic flux through it, then the hole is going to have an edge state going around it. Okay, but since it has a finite circumference, the edge states are going to be quantized, finite size quantized. Okay, and so the interesting question is when you do the quantization, do the quantized states hit zero or not? Okay, they have to be. It has to be particle-hole symmetric, but there are two possible particle-hole symmetric ways it could be. It could either be like this or like this. And of course, when the flux is zero, then there's not going to be any zero modes. There's a gap if the flux is zero. So there's this picture. When you have a odd number of flux quanta, then it shifts it by half, and you get a zero mode. Okay, and now of course you're also going to have the higher states. Okay, especially if the circumference is big, and so there'll be lots of low energy states bound to this vortex. And there's an old theory of this, going back to Caroli and de Gennes, for the sort of bound states on vortices. Okay, when delta is much less than EF, when the gap is small compared to EF, then these are pretty finely spaced. Okay, and so it's a challenge then to resolve this in a vortex. Okay, but there are experiments that claim to be able to do this. Okay, so now I want to, I think this is probably as far as I'm going to get. So I want to just, so we talked about time reversal symmetry, right? And remember, the physical time reversal symmetry has the property that it's anti-unitary and it squares to -1. That's what gives us Cramer's theorem. And we talked about the intrinsic particle-hole symmetry. It anti-commutes with the Hamiltonian. It squares to +1. Okay, and so there are several. You could also imagine that you have a time reversal symmetry that squares to +1, or you could have a particle-hole symmetry that squares to -1. So all these possibilities, or you could have both of them. And so if you consider all of those possibilities, then a very rich and beautiful mathematical structure emerges. Okay, and so I want to consider, the possibility of having anti-unitary time reversal symmetry that commutes. It squares to either + or -1. The anti-unitary particle-hole symmetry anti-commutes. It squares to + or -1. And then I could also have a unitary symmetry, which is like the product of these two. Okay. So there are all these possibilities that you can have, and these possibilities have mathematical labels attached to them, and these labels are the same labels that one uses to describe the symmetries in random matrix theory. Okay, and so so there's this Altland-Zirnbauer classification of random matrices according to their symmetries, and it's the same. That's where this notation came from. So one can work out what the topological classes for all these kinds of symmetries are. And I explained to you the top two rows. These are the ones without any anti-unitary symmetries. Okay, and it has this d to d plus 2 bot periodicity. Okay, so the ones with unitary symmetries, there are 8 of them. Okay. And the pattern of topological classes has a bot periodicity under dimension goes to dimension plus 8. Okay, and it has this rich pattern now. So we've met a number of these states. So class A2 is the class where you have time reversal symmetry. It squares to -1, and there's no 0 means there's no particle hole symmetry, no unitary chiral symmetry. So then in 2 dimensions you have a Z2 topological insulator. In 3 dimensions you have a Z2 topological insulator. In 4 dimensions you have a integer second Chern number. Okay, and actually one interesting fact about the second, the 4-dimensional Chern insulator is that it is compatible with time reversal symmetry. Unlike the 2-dimensional Chern insulator that has to break time reversal, in 4 dimensions, the Chern insulator does not have to break time reversal symmetry. So there's an integer. This is the second Chern number. And so then, so we met the 1-dimensional topological superconductor. That's class D, where the particle hole symmetry squares to +1. And in 2 dimensions, there's an integer because you can have an integer number of chiral Majorana modes. Okay, and so one can work out all the other classes. Okay, and there's a rich mathematical structure. It has something to do with something called K-theory, which I confess I don't really understand what K-theory is. So that's in there. There are many levels that one can understand the mathematics of this on. Okay, and I'm sort of in the intermediate level myself. In order to understand the physics, you don't really need to understand the highest levels of the mathematics. I tend to, my understanding of these things is the pictures that I draw, okay, which makes me feel like I understand what I'm doing. Okay, all right, so I think I'm out of time. I was going to tell you a little bit about how you could realize topological superconductivity by combining ordinary superconductors and topological insulators. But I think since it's just about 10 o'clock, I should finish, and then we can keep on time. So I think I'll finish with that. So thank you.
Are there any questions? Please wait.
Thank you for the talk. In which situations do you get a particle hole operator that squares to +1?
Right. Okay. So no. So in the usual case, the particle hole squares to +1. So you're asking in which case do you have it squares to -1? So what you need in order for that to be the case is you need an extra symmetry. So let me tell you a simpler version of your question, which is you could ask, how could you have time reversal square to +1? Okay, which is and there, if you don't have spin-orbit interaction, okay, let's imagine in carbon, the spin-orbit interaction is really weak. So it's a very good approximation to ignore the spin-orbit interaction. Okay, so then you can think about the time reversal symmetry for each spin, basically, and that gives you a time reversal operator, which is just complex conjugation. It doesn't do anything to the spin, and that squares to +1. Okay, so it's the extra symmetry that allows for this other sign of the time reversal. And so, and it's the same story for the particle hole symmetry. So if you have absence of spin-orbit interaction, okay, then well, so what I'll say, so when we did this, then we sort of we have two copies. You know, we have the upspins and the downspins. So the real system is doubled, okay? And it's the same, and whereas the particle hole symmetry is just only acts within one of the partners, and it's the same story with the particle hole symmetry. So so if you don't have spin orbit interaction, then you can treat sort of half the problem as if it has the particle hole symmetry, which squares to -1. Okay, and so that's a way that you can get these other classes. Okay, but they're not. You know, it's only an approximate symmetry, right? It's not a fundamental symmetry. The fundamental one is, you know, time reversal squares to -1 and particle hole squares to +1. The approximate symmetries are the other ones. Okay, yeah.
Yeah, so we got the particle hole symmetry from the mean field theory in the
Yes.
superconductor. But then if we look at fluctuations about the mean field theory, even if they're irrelevant, they're still there. And why don't they break the symmetry?
Well, I mean, the thing is that the symmetry is, you can't write down the theory without having the symmetry. So it's really, the symmetry is baked into the way you're writing the theory. So it's not like there are terms you can add to the theory that violate the symmetry. You can't, you know, putting in fluctuate, you know, so you can expand about the, you know, the mean field theory. Okay, so you can try to, you know, introduce interactions, but those aren't going to be terms that violate the particle hole symmetry.
Okay.
You can't write them. You can't add them. So doing fluctuations doesn't add terms that violate the symmetry, unlike regular symmetries where you could do that. Yeah.
Final question, maybe last question. We know that for 2D topological insulators, we can classify the phase using the Pfaffian of the Stewing matrix, which is built from the eigenvector of the Hamiltonian.
Yes.
But in the Kitaev chain, for example, I can use the Pfaffian of the Hamiltonian at the trim point.
Yes.
So I was wondering if there is a connection to these two ways, and like for example, because in the case of topological insulator, we can use inversion symmetry to simplify the equation of the Pfaffian to just count the parity,
yes.
because we can resolve this labeling ambiguity.
Right.
But can we do something like that with the Pfaffian for a
For
topological?
superconductors? Yeah, I think so. I think so. Yeah. Now, so the thing I don't know how to do is I don't know how to, you know, do the kind of analysis that you're talking about, you know, for all classes at the same time. The only thing I know how to do is to sort of do each class one at a time and understand how to formulate the you know, the Z2 invariant. So I didn't spend time talking about how you actually compute in general these invariants. But the only way I really know how to do it is to do each class sort of, you know, think about each class one at a time and understand how to do it. I don't know a general procedure, and my feeling is that, I mean, there probably is a general procedure, but it requires a more sophisticated level of mathematics where you know, you spend all your time learning the mathematics and then you forget about the simple picture that you draw. So yeah, I think that's all I have to say about that.
Okay, great, thank you. Let's thank Charlie again.
Okay, thanks.